All right, so today we're going to talk about how to use logs to solve exponential. And when we do this, we are going to use some rules that we have talked about before. So when you solve an equation when your variable's in the exponent, so far we have used the same bases to solve. However, sometimes numbers can't be written with the same base, so we can't always use this in order to solve exponentials. So, because logarithms are exponents and we know a little bit about them, we can do a couple of things. So, when b is greater than 0 and b can't be 1, if log base b of x equals log base b of y, then we know that x has to equal y. So if x equals y, then we can also take the same base log of both sides in order to say that that is true. So these two are just like the opposites of each other. So we can use this property to solve exponential equations. We can first get the base by itself, then we can take the log or natural log of both sides. As long as we use the same base, it doesn't matter what you use. We use log and ln because those are what's on our calculator. Notice where the variable is. It is in the, it's going to be in the exponent. And so then we can bring it to the front to make it the coefficient of the log expression and isolate the variable in order to solve. So the first one, we're going to use common log as an example. So I'm going to go ahead and add 16 to both sides. My goal is to get the base, which is this 4 right here, by itself first, and then I can go from there. So that's why I added the 16. We do like PEMDAS backwards when we're solving. And then 3 times 4 to the x power. I'm going to divide by 3, so that's 4 to the x equals 32. And then I'm going to take the common log of both sides. So this is where if I have x equals y, so I have x equals y, then I can say take the log of both sides, which causes the x to now be in the exponent. So this is what I'm talking about right here. This little x is in the exponent, which I know according to log rules that I can move that to the coefficient. So I'd have x log of 4 equals log of 32. And then from there, I would divide by log of 4 to get the x by itself. So I'd have log of 32 divided by log of 4, and I would type that into my calculator, and I end up getting that x equals 2.5, okay, or 5/2, whichever one you want to write it as. Now, this one, technically, if you look at this step right here, this 4 to the x equals 32, I can technically write those to have the same basis. So we did that on purpose to show you side by side that you can actually solve this either way. So I'm going to go ahead and start with 3 to the 4x, 3 times 4 to the x power equals 96. Divide by 3, which would give me 4 to the x equals 32. I can now rewrite these to have the same basis. So I'd have 2 squared raised to the x power equals 2 to the 5th. So 2x equals 5. X would be 5/2, which is 2.5. Now, that just shows you that this is two different ways to do it, but you get the same answer. So you can solve any equation, even if you could write it with the same basis, using common logs and natural logs, but the opposite is not true because sometimes we can't make them have the same basis. So let's try one with using natural log. So for this one, get the base by itself, which our base is e in this case. So I'd say e to the negative 2x equals, if I divided by 4, I would get 25. And then if I take the natural log of both sides, I now have my negative 2x in my exponent, which I know I can bring to the coefficient. And then this awesome thing happens right here. We know that the natural log of e is actually 1. So from there, I just have negative 2x is equal to the natural log of 25. And then I just divide both sides by the negative 2. And I get my answer, which is negative 1.609. Okay. Now, notice that x is in the exponent. So some of you are probably like, you can't get a negative answer, Miss Byer. You actually can, because that's the exponent. It is not the base or the argument. So we're okay. So the benefit of using natural logs is that the natural log of e is equal to 1. Okay, and so when you take the natural log of each side, when you have e as a base, well, then you're just going to get 1, and it's kind of one less step right there. All right, so let's practice a few. This first one, I'm just going to take the log of both sides. This one's real simple. And then I'm going to bring the x to the coefficient. And divide by the log of 6. I would type that in my calculator, and my answer is 2.804. Remember, we round to the thousandths, so that one rounded up. All right, the second one, same type of deal. So you're going to take the log of both sides. Log of 10 equals log of 2 to the x. Now, guess what? This one is awesome. We can bring the x to the numerator, but we also know something cool about log of 10. Well, we know that the common log has a base of 10, right? So this is technically base 10. Log base 10 of 10, we know by our exponent rules, is 1. So really, I'm just taking both sides, dividing by the log of 2. So I'm taking 1, dividing it by the log of 2, and I get 3.322. All right, now the next one, we've got an e, so I'm thinking to myself, I'm probably going to take the natural log of both sides because I have base e. I can even see it still right here. Natural log of e equals 1. So then I've got the natural log of 2981, okay, 2,981. Bring your x to the coefficient, so that's x. We know that the natural log of e is just 1, so technically x equals the natural log of 2,981, which is 8. And that would be my answer for that one. It's really like 8.0000, so it just ends up rounding to 8. All right, let's take a look at number 4. I'm going to go ahead and get the base by itself first this time, so I need to divide both sides by 3, which gives me e to the 3x power equals 4. And then I'm going to take the natural log because I see a base of e of both sides. I'm going to bring this 3x to the coefficient. I know that the natural log of e is just 1, so I've got 3x equals the natural log of 4, and x is just going to be natural log of 4 divided by 3, which is 0.462. All right, next one, a little more steps to get the base by itself. So I'm going to subtract 10. That gives me 240 equals 3 times 7 to the x power. Then I'm going to divide by 3, which gives me 7 to the x power equals 80. I'm going to go ahead at this point, I have the base by itself, so take the log of both sides, bring the x to the coefficient, and then divide both sides by the log of 7. So x is going to be the log of 80 divided by the log of 7, which is 2.252 for that one. All right, last one today, and I see a base e, so I'm thinking we're probably going to use a natural log on this one. I'm going to go ahead and add 3 to both sides, which gives me negative 1/5 e to the x power equals 20. I'm going to multiply by the reciprocal of negative 1/5, which is negative 5. That's going to give me e to the x equals negative 100. And then I'm going to take the natural log of both sides, but there is an issue. Here's my issue. This right here is a negative argument. We cannot have a negative argument. So, argument has to be greater than 0. Okay, that's not. So, this one is going to be no solution as our answer for that one. All right, so today we've gone through the steps to use logs to solve exponential equations.